Okay, so I mentioned this reaction book, so we're going to start adding reactions to that. The first one, hopefully if you have your book, if not you can print it out after lecture and then add it to there. There's 4 different categories that we keep in this class for reaction types. The first one is a functional group transformation, and that is where we're changing one functional group to a different one. So if we're changing from an alkyl halide to something else, that's a functional group transformation. We also have carbon-carbon bond-forming reactions, oxidation reactions, and reductions. But today we're just looking at the functional group transformation. So usually I'll have what kind of reaction it is on the left side here in gray, and this happens to be page 5 in your reaction book. All right, so I keep track of these reactions by chapter. So this is from chapter 7, and the starting material is an alkyl halide with a leaving group here, and this is going to include a nucleophile, and this is our SN2 reaction. So this is wedged, and other things that can be here are a benzyl with a leaving group, a aryl leaving group, or allyl, sorry. And then you have the primary or secondary. So you can do these reactions with the benzylic, the allylic, primary, or secondary, and those all say Lg for leaving group. So we have our R, and then the product that is formed changes to stereochemistry, and we form a bond with the nucleophile. So selectivity indicates what kind of stereochemistry there is there, and the products that we can get are going to have inverted stereochemistry. And then I just have some notes here. Our leaving groups can be X minus, so any of the halogens. And then OTS is that tosyl group. And the nucleophiles that we can use for this reaction are OH minus, OR. We can use SR minus, so that's a thiol or a sulfur, so something like NaSR. And we can use SH minus. So sulfur acts a lot like oxygen. And then for this, I also put a note here that we want a polar aprotic solvent. All right, that's the first reaction. The next one is with a leaving is the SN1, sorry. I'll start with the leaving group. And I have this on a tertiary, but this could also be the benzylic also, the allylic, tertiary, and secondary. We have nucleophile. This is an SN1. And there's my mixed stereochemistry with a new bond to the nucleophile. So this gives us a racemic mix. And racemic means that half of your product is staying the same stereochemistry, the other half is mixing it. So for this one, our leaving group options are X minus, OTS, or water. So halogens, the tosyl group, or water, and our nucleophiles are neutral ones. things like alcohols. So R can be CH3 or CH2CH3 or water. They can also be HX. So hydrogen bromide, hydrogen chloride, those types of things. And our solvents here are polar protic. All right, so there's two, and then I have two more reactions on this page. These are going to be this is another SN1 reaction. This involves an OH. So we know that this is a bad leaving group. But we can make it a better leaving group by adding HX. And that will protonate that alcohol and make it water. And then once the water leaves, which we know is a good leaving group, we can do that substitution. So this is also a racemic mix. So you can use HX here. All right, sorry about that. Okay, so just to recap everything I just said that there was no audio for. Again, thank you for rejoining me and standing by there. The OH group, we have the tertiary OH group. Even if it's tertiary, it's still OH is a bad leaving group. We have HX, which can be Cl, Br, or I minus, and that will do a proton transfer first to make that OH into a better leaving group. And then the water will leave. X minus can then attack at the carbocation that forms. If you want to do an SN2 reaction with an OH group, we can make it into a better OH group and use tosyl chloride, which will put an OTS group on there. And we know that is a good leaving group, so that will allow you to do the SN2 reaction with the OTS. Okay, any questions there? All right, again, welcome back. Again, I apologize for the technical difficulties. Thank you for rejoining us here. The next set of reactions are the carbon-carbon bond forming reactions. This starts on page 13 of your book. And let's see, this is still chapter 7. And these are the same reactions pretty much, but we're forming a new bond to carbon, so that's why I have them in a different category here. So this is our leaving group, whatever that may be. And our nucleophile is going to be Cn minus, and that might appear as NaCN. This will be your SN2 reaction. And we get inversion of stereochemistry. This is the Cn, and this is inversion. You can do this with the tertiary. This is going to be an SN1. And instead of Cn minus, we do this with HCN. And you get the squiggle racemic mix here. And just like we saw before with the OH group, we can have an OH here. We use HCN. That's going to protonate that alcohol and make it a better leaving group. So then the water can leave, and then the HCN is, or the Cn minus there, is welcome to do the attack. All right, any questions there? So those are the couple of reactions for chapter 7 in the reaction book. And we'll have more to add on Wednesday when we start chapter 8. All right, so there's 4 main factors that will determine whether a substitution reaction will happen by an SN1 reaction or an SN2 reaction. and we're going to look at those closely here. And I'm going to go a little bit old school to try to reduce the technical glitches here. So we're going to go pen and paper. So hopefully you can all see that screen there. And this is the reaction book that you have access to on Moodle. Hopefully you have printed it out so you can use that. So we're going to look at the first page here, which is these things with the cats. All right, so let me see if that's better without the lights. Okay. All right, so we have the two comparisons. There's two sets of the cats there. In the first one, we can see there's a cat sitting, you know, fairly happily, and then it leaves the bed, and then the other cat comes in to take its place. And then we have a cat sitting here, and then the other one is violently attacking that one so that it leaves, and now that it's occupying the place. And after we look at the comparison of the two, we know that the one where the gray cat, which is the leaving group here, leaves, that is the SN1 reaction, and this is the SN2 reaction. All right, so you can think of this also as if you're a college student and you left home, and presumably at the beginning of last year, or at some point in your life, you left home of your own accord to go to college or to do whatever else. You left your home, and then maybe something took your place after that. Or you can be like my brother, who is, I think, 36 years old now and still lives at home with my mom. He just needs to have my mom to kick him out of the house here. But so that's the difference between the SN1 and the SN2. So mechanism-wise, they differ very much. So for an SN1 mechanism, it's two-step, but it can be multi-step if there's proton transfers involved. So the mechanism of the SN1 reaction is two-step, or it can be more again if there's proton transfer. The SN1 or SN2 reaction, is one-step. All right, and then a carbocation. SN1 reactions do go through carbocations, so we can have a rearrangement possible. And there is no rearrangement possible in the SN2 reaction. All right, and at any point, if you have questions about any of these comparisons, please in the chat to privately to me or to everybody, or you can chime in audio as well. All right, the big barrier for the SN1 reaction is forming the carbocation. Which is that C+. So the leaving group has to leave in order for the SN1 reaction to happen. And the barrier for the SN2 reaction is sterics. And the alkyl halides or electrophiles that we can use for the SN1, SN2 reactions, these are usually an L and a leaving group of sorts. So we have the benzyl carbocation, which will be faster than an allyl. Which is faster than the tertiary carbocation, which is faster than secondary. So this tertiary one right here, this one will only do SN1. So we cannot do SN2 on a tertiary carbocation. So these are the electrophiles that we're going to see for that one. For SN2, we use the benzyl. So benzyl can be SN1 or SN2. So I'm just going to put the leaving group there. That one will be faster than the allyl. So an allyl is the carbon next to the double bond. we have primary and then secondary. And this one will only do SN2. So if we see a tertiary alkyl halide, we know that's going to go SN1. If we see a primary, that has to go SN2. Any of these other ones, we'll have to look at other categories here. All right, for nucleophiles for SN1, we just need an OK nucleophile. So these are things that are like water and an alcohol. And we only need an OK nucleophile with the electron lone pairs because the carbocation has already formed, which is our really good electrophile. So we just need something in its place to attack there. For an SN2 reaction, we need to have a fantastic nucleophile. Okay, and sometimes I think of nucleophiles kind of like pizza. If you are super, super hungry, just about any pizza will do. You're okay with Totino's pizza or something frozen from the gas station because you're starving, and anything will pretty much work there. But if you are not that hungry, you're going to be a little bit more particular about your pizza. So for SN2, that's where you're not that hungry and you want to be particular. So the nucleophile is the driving force here, so we need to have a really good one. So the Little Caesars hot and ready may work for your SN1, but not so much for your SN2. For your leaving group, however, that's kind of the opposite. For SN1, you need to have an excellent leaving group. If you're going to send yourself out into or leave the house, you should be prepared. You want to be able to stabilize your negative charge. So these are examples of the leaving groups. And this big one here is the tosyl. And the leaving group is the driving force for the carbocation to form. And then for the SN2 reaction, because the nucleophile is the driving force, we just need a leaving group to be there. So any old leaving group will do. So you can have the X minus OTS. Questions so far? All right, the solvents for an SN1 are polar protic, which means they can donate a proton. So they can donate that H+. So these solvents are water and alcohol, so ROH. Or you can have acetic acid, which can be written CH3CO2H. That's also the component in vinegar. So this solvent will support an anion and a cation. So that means that when the leaving group leaves, that solvent is going to stabilize the positive electrophile, and it will also stabilize the nucleophile. For an SN2 reaction, we want a polar aprotic solvent that does not contribute a proton. These solvents are acetone, DMSO, which looks like acetone but has a sulfur. We can have acetonitrile, DMF, which is an aldehyde with a nitrogen on the other side, and then there's two methyl groups there. So these solvents will stabilize the cation only. They only want to stabilize the positive charge, and that will make, or any partial positive charges, and that will make the nucleophile that much stronger. Questions there? All right, and for the stereochemistry in an SN1 reaction, we get a racemic mixture. Because the nucleophile can attack or hug from both sides of the carbocation. So 50% will stay the same stereochemistry. And then we'll get 50% inverted. In the SN2, we have inversion of stereochemistry. Because we have backside hug or attack. So this is still on page 5. We're on the functional group transformation page. And this one is from chapter 8. And this can be for alkyl halides that are tertiary. They can be secondary or primary. But there needs to be a leaving group there, which can be the halogen, or it can be a tosyl group, something that's a good leaving group. And then we use a base.
Mommy.
This will do an E2 reaction. So when we have that base, which we're going to assume here is a small base, that's going to do an elimination and pull off this hydrogen over here. And we get the double bond forming right there. So this is the Zaitsev product, which is the most substituted alkene. So the most substituted being it's going to have the most number of substituents off of there. And it will also be the most stable. All right, the best things to use for bases in this condition, or in this reaction, which we'll see also tomorrow, is sodium hydride. So the hydride in this case is one of the rare times that we'll see H as an H minus, is when it's paired up with sodium. We can use DBU or DBN. And you don't have to worry about the structures, just as long as you know DBU and DBN are bases. for this reaction, we also need to have an anti-coplanar hydrogen. And that means an H that's on the opposite side of the leaving group. And we'll see that a little bit later. All right, any questions on that E2 reaction? So that's with a small base. All of those bases, the NaH, Dbu, and Dbn, are small bases. And with tertiary, secondary, and primary substituents, those are going to go E2. This is another E2 reaction, and this is with tert butoxide. It's also sometimes written as TBUOK for tert butyl butoxide. So if you see TBUOK, that's the same thing as this structure right here. And that is going to go for the least substituted alkene. This is the Hoffman product. Any questions on that reaction? All right, and then we have one more. And we'll come back to the recap here in a second. I'll probably repeat some of this stuff. This is an E1 reaction. And this would happen with water or an alcohol. And we're going to get the Zaitsev product and also the SN1 product. And we'll talk more about that tomorrow there. That's the situation with that. So E1 products are actually very hard to come by, or that type of reaction. And this gives you a Zaitsev product. So if you notice on that first line of the E2 reactions, that we can do an E2 reaction with tertiary, secondary, or primary. Those are the one-step reactions. The E1 has to go through a carbocation, so we have competing reactions with the substitution and the elimination. All right, is anybody still jotting things down? They need the screen for a little bit longer. Speak now or forever hold your peace. All right, so this will be in the chapter 9. And this is on page 5 of the functional group transformation page where we've already been adding reactions. The first one I'm going to add is just the generic alkene. This one is going to be just an asymmetric one. So we can see where the regiochemistry falls. If we have a halogen where X equals Cl, Br, or I, we add X to the more substituted side, and H goes to the carbon that has more hydrogen. So this is a Markovnikov product. So that one goes to the Markovnikov. If you want to switch that regiochemistry to the anti-Markovnikov. We have the same alkene. We're going to add peroxide to that reaction. So R being other R group. We use the same HX. So we have H over here. So it's not necessary to draw the hydrogens in. I'm just drawing them here to show you where they go to, in case you were wondering what happened to them. So this is the anti-Markovnikov. Another note that I should make in the reaction we just did, the one up here, is that with the HX, there's a rearrangement possible. And that's because it goes through the carbocation. In the one with the peroxide, we won't see a rearrangement because there's no carbocation. That one goes through a radical mechanism, which we don't need to worry about right now. All right, next we have another alkene reaction. This one involves water and a catalytic amount of acid. So we could get two products here. In the first one, your hydrogen would go to the carbon with less or more hydrogens. The OH goes to the one with more substituents coming off of it. This will be the minor. The major one would occur from a hydrogen adding where it was going to add anyways, and then the rearrangement. So you could have this product for the one with the HX as well, or similar. So this is Markovnikov, and a rearrangement is possible. All right, so those were the reactions for 9A. For 9B, which I just kept in the 9 chapter here, I have the same generic alkene. And this one involves mercury. Mercury acetate plus water. The water is going to be what it adds to the alkene at the end of the day here. So this one is a way to get an OH on the more substituted carbon at the Markovnikov position. And this one has no rearrangement possible. And that's because it doesn't go through a carbocation. So that'll be a nice reaction where we don't have to worry about that. If you're trying to add an alcohol to a secondary position, and there's a tertiary next door, we don't have to worry about it rearranging. However, if you had a tertiary position, you can go ahead and use the acid and water without it worrying about it rearranging there. But this mercury is a way around that. If you want to put an alcohol on a primary carbon, we do a hydroboration. And the OH minus that is added in the second step, so usually sodium hydroxide is the source of the alcohol. And these add syn to each other. The H does anyways. The H and the OH are added on the same side to each other. So this is an anti-Markovnikov. And the H and the OH are syn to each other. So you would get this product plus the enantiomer. So if you're really keeping track, one of these H's on the BH3 would be in orange as well. So that's where the H comes from. And then the OH comes from the sodium hydroxide. If you add a halogen here where it's X2, where here X equals Br or Cl, not iodine or fluorine. Iodine would be too slow to react. Fluorine is too wild. At X2, we're going to add both of those halogens in an anti-addition to each other. So that is an anti-addition. And then the last one for this page is if you have that halogen in the presence of water. This is a halohydrin reaction. So the alcohol is going to go to the more substituted carbon. The halogen will go to the less substituted carbon. So you get this product plus the enantiomer. This one is an anti-addition. And the OH goes to the more substituted carbon. Any reaction or questions on the reactions that we just added? So I'll give you a minute to jot those down. The next reaction that we're going to do, and the last one for today, is going to be on the reduction page. So I need to find that page in my book here. All right, so the reduction page for me starts on 19. So same generic alkene. This one's going to involve hydrogen with any metal catalyst, so it can be palladium, platinum, or nickel. We have H2 gas. And these reactions usually are done with hydrogen gas inside of a balloon that is put onto a flask. And these will add to on the same side to each other. So this one is a syn addition. So if you needed to do anything where you had a double bond, and next chapter we'll see triple bond, you need to reduce that to the alkane, back to single bonds, you can use hydrogen with a metal catalyst. All right, questions, or is anybody still writing? All right, looks like nobody is still writing. And we're going to add reactions from chapter 9, part C. And we're going to start with our generic alkene. This is on page 6 of the functional group transformation. So it's kind of that same alkene that we've been using. We're going to add R, which is our generic carbon, CO3H. So this is a peroxy acid. So it could be, the R can be anything there. So these are the reagents in that reaction. And we're first going to form an epoxide, which is a 3-membered ring with an oxygen in it. So if you add the RCO3H only, that will make the epoxide. And then after you follow it up with water, that's going to open up the epoxide to form a diol. And the alcohols will add anti to each other. So we'll get this one plus the enantiomer of that one. So this is an anti addition. All right. Any questions on that reaction? This is an anti-addition. All right, the next one, and the next two actually give a similar product, just different options for reagents here. Another generic alkene. This time it's osmium tetroxide. So there's 4 oxygens. And you can use NMO or Na2SO3 to work it up. This one will give you a syn diol. So if you want your alcohols on the same side as each other, you would use the osmium tetroxide. So you would get this product plus the enantiomer. And this will give you a syn diol. So they're both on the same side. So on paper, osmium tetroxide works fine. In the lab, if you were on a budget, we might use KMNO4 instead. So potassium permanganate will do the same thing. And we would follow this up with sodium hydroxide. So you get that one plus the enantiomer. And this is the syn diol. So those are 2 ways or 3 ways to get 2 alcohols next to each other. One method with the RCO3H that gives you an anti-addition of the alcohol. And then if you want the alcohols on the same side, then we use the KMNO4, which is much less expensive. Or you can use the osmium tetroxide. Any questions on any of those reactions? All right, the next reaction we have in my book, I think it's on yours also, is page 17, which is where the oxidation reactions start. And oxidation is loss of hydrogen or gain of oxygen. This is 9. So we have our alkene here. And this reagent is ozonolysis, or ozone, O3. And we work that up with DMS. And what that does is it cuts this double bond in half. So you can take a scissors, cut on the dotted lines, and then separate your 2 pieces. And we get oxygen and an oxygen there. So your two products are a ketone, and if you want to draw the hydrogens in here that were there before, you can, and you get the aldehyde here. This particular reaction is a reductive workup. And that will give you the aldehyde. If you had something, another reagent instead of DMS, you can do an oxidative workup where you have carboxylic acids, but we'll look at that more in the next chapter. Any questions on that reaction? So ozonolysis, which is that smell from the photocopier that you get, is a way to cleave double bonds in half. So if you're looking for reactions where you end up with this ketone or an aldehyde, or in a case where you lose a carbon, you would want to look for ozonolysis there. All right, questions there?
Where's Dad? Where's he going?
All right, so for chapter 10, we're going to start with how to make alkynes. And there's two ways that we can make them. One is from a dihalide. Actually, they're both from dihalides. This one involves a dihalide on opposite or on two different carbons. So this involves excess NaNH2 in ammonia. And we need that second step of the water workup in order to protonate. So the base will just keep taking protons, and then once you form the other one, the acetylide or the alkyne, you get the negative charge, and then the H2O will give the proton. So when you do this reaction, we form the alkyne. So that's one way to form the alkyne, and the XS equals excess. And so that you have extra reagent around, you want more than one equivalent. So we just write that as excess. And so XS does not stand for extra small. It means that there is more of it. And NaNH2 is a bit strong base. All right, and that compound we know how to make from an alkene plus Br2. The other way to make an alkyne involves the geminal dihalide. So both of those Br groups are on the same carbon. And it's the same reagent. So the same excess NaNH2, NH3, H2O, and we'll get the same product there. All right, and then the next reaction is once we make that or have an alkyne, so either have one or if you needed to make one, we can add HCl to that or HX. This is one equivalent, so that does not say leg, that is one, the number one, and then EQ for equivalence. We get the alkene. The halogen goes to the more substituted carbon, and the hydrogen goes to the carbon with more hydrogens. So in terms of selectivity here, this one is Markovnikov. All right, and that's with the terminal alkyne. This is also a terminal alkyne. Here we're going to add HX again. But now this is in excess, so there's lots of it around. And that once the X forms like it does in this reaction here with the 1 equivalent, the HX can react again, and that X will still go to the more substituted, and the H will go to the carbon with more H's. So this is still a Markovnikov reaction. So 1 equivalent gives us 1 halogen, and XS will give us 2 halogens. So this is a way to make that compound there if you needed to do the geminal halogens there. If we want to switch the regioselectivity to the anti-Markovnikov, we do the same thing that we did in the last chapter. We have HX, and we add that peroxide. So if I have just the 1 equivalent here, I get my alkene, my halogen goes here, the hydrogen goes there. That one is anti-Markovnikov. So the product of the HX here with our OR, the 1 equivalent, is an alkene. So that's just going to react 1 time. If we do the excess like we did above, we'll get 2 halogens here. This is anti-Markovnikov. So if we have 1 equivalent of these 2 reagents, the HX1 equivalent, HX1 equivalent with peroxide, we get an alkene as the product. If you have an excess, that reaction will keep going and give us the alkane. All right, questions on those ones so far? All right, the next one, we have H2SO4, so sulfuric acid, in the presence of mercury sulfate and water. This starts to do the same thing as we saw with alcohol. So we first get the alkene here with the OH. That's an intermediate here. This is called an enol, the ene from the alkene and the ol from the alcohol. And that will do kind of a proton shuffle dance that's called tautomerization. So our carbon skeleton stays the same. The H from the hydrogen, or the alcohol here, will jump over to this carbon so that we can make a ketone. And this one is also Markovnikov. So it'll first go to the enol, and then it'll do tautomerization to get to the ketone. If we use an R2BH with THF, OH minus, we'll also get an enol here, except our OH is on the end. Here's our enol, and that will also do the tautomerization. My carbon skeleton stays the same. The hydrogen shuffles over to here, and then I get my carbon double bond oxygen, and that will form an aldehyde. So this is the anti-Markovnikov product. Other things that, or things that you can use for the R2BH, include the 9-BBN or diisoammoniborane. So if you see either of those two reagents, that's going to make an aldehyde from the alkyne. If we use BH3 like we did with the alkenes, we'll just get a holy mess of different products. So you want to stick with where there's only one hydrogen source there. All right, the next reaction, Br2, this is one equivalent. That's going to make an alkene. And I add Br on opposite faces to each other. So this is an anti-addition. Just like we saw with the alkene, we added Br on different sides of each other. And if we add an excess, we'll just add 4 BRs. So you'll get this alkene first, and then the Br2 will react again if you have an excess. And that's also still an anti-addition. All right, any questions on those reactions before we go to the next type of reaction? All right, so while you're finishing up there, the next place that we're going to add a reaction is to the carbon-carbon bond forming page. Okay. All right, so far we've only added from chapter 7, so now we're going to add a chapter, what are we in, 10? Chapter 10 reaction. And this one only works for terminal alkynes. And that is because we need that acidic proton on the end there. So this involves that base NaH2 in ammonia. And this can be any alkyl halide. So we'll have a carbon group plus a leaving group, where X is whatever leaving group. So any of those Br, Cl, or I. And R must be primary or secondary. So what happens is the NaNH2 is going to pull off the proton right there, that terminal proton, and these electrons will go on to the carbon to make a negative charge. And that negative charge can then attack the R. It's going to do an SN2 attack there, which is why we need a primary or a secondary, and then it will add that R. So you just need a good leaving group and then a primary or secondary carbon there. You can add just about any carbon group that way. Any questions on that one? All right, then we have a couple, I think oxidation is next. Yep. So we have a couple of oxidation reactions to add. All right, and this is chapter 10. All right, this is ozonolysis. So we're adding O3. If you look above here, when we added O3 to the alkene, that cut the alkene in half and then put oxygens there. We're going to do the same type of thing here, but the water is going to act as an oxidative workup. So we get this O here, but we also get an O on the other part of the carbon. So this is an oxidative workup. So we cleave that double bond. We get 2 carboxylic acids. So that triple bond, 2 of those things go to form the carbon oxygen double bond, and then we get an OH there. So you end up with 2 carboxylic acids if you have an internal alkyne. If you have a terminal alkyne, so one that's on the end, and we do the same reaction, we end up with 1 carboxylic acid and then CO2. This is also the oxidative workup. So if we do ozonolysis on the internal alkyne, where there's R groups on either side, we'll get 2 carboxylic acids. And then ozonolysis of a terminal alkyne, we get 1 carboxylic acid plus the CO2. Any questions on that one? All right, and then next we're going to the reduction page, which is page 19. Just put it right under here in case you're still writing. We have a couple of different reduction reactions to write. If we have excess of H2, we will reduce our alkyne all the way to the alkane. So you won't be able to stop the reaction. Even if it's just one equivalent, it's almost impossible to do just one equivalent. So if you remember me mentioning doing these reactions with hydrogen balloons, if you could magically measure out one equivalent of hydrogen gas into a balloon, that's pretty amazing. But so this would just go all the way. If you want to stop at the double bond and get these Z alkene, oops, we would use H2, but add Lindlar's catalyst, which is a poison, and it will stop the reaction at the double bond. And that gives you the Z alkene. So it's still a syn addition. And if you want the E alkene, you would use Na and H3. So that's liquid ammonia. and that will give you the E alkene. And that goes through a radical 1 electron mechanism. Is there any questions on any of those reactions? So we've added a lot of things to our synthesis toolbox in this chapter. We can now make molecules longer, shorter, and change functional groups to manipulate them in different ways. All right. So we're on the last reaction of page 6 here. And we just have 3 to add today. The first one is adding, I just have, what is that? 2-methylpropane. So this can be any alkane. We add chlorine in the presence of heat or light. So H nu being light, or you can have heat. And with chlorine, you're going to get a couple of different products. The chlorine is very reactive and it will just go anywhere. So it can go to this carbon or this carbon here. It's going to result in multiple products. So this is why CFCs can be dangerous, because those chlorines can react with a lot of different things. So we'll get different products with the chlorine. It's not very controlled. It just kind of attacks anything that it wants to attack. All right, so I'm just starting a new page here. This is page 7. Sorry, I should specify this is on the functional group transformation page. And the same starting material, if we add the light and heat with Br2, the Br is going to the most stable position, which is the tertiary one. So that one you're mostly going to get one product. So the chlorine will go to several different places, and it can really go to any one that's going to where it's different. I only had 2 products on that line above just because the molecule had symmetry to it. But if it was asymmetric, then it would go to any of the positions there. For bromine, it's going to go to the most stable one. And then the last reaction is one with where a double bond is involved. So you have an allylic position. We add to the NBS. And that is N-bromosuccinimide. That will add to the allylic carbon, which is the carbon next to the double bond. And because we have resonance here, it will add to the other side as well. All right, so if we draw a resonance structure of this double bond here, these electrons can come over here, which is where I've drawn the orange one, and that will produce the radical on that end. And so then the BR can attack there. So we have two products when NBS is involved, and it's not symmetric. All right, any questions on those reactions? All right, so if you are not continuing on to organic 2, then that is the end of your reaction book. If you are continuing on, we'll be filling that bad boy up next semester. All right, any other questions before we go to the CPA questions?